So hello everyone to our video presenting our project that is about an application of computer vision. It is basically image classification using machine learning. In this project we have built convolutional neural network for image object classification using Keras, which is a free open source high level API used for neural networks. In this project we use for the dataset we use CipherCAD, which stands for fundamental benchmark in this field of machine learning. The dataset comprises 60,000 color images, each 32 by 32 pixels. And this is our project. Let's move now to our code, starting by this code. And I will leave the floor to Mohammed.
So first of all, we have from Google Colab import our files, and then we download our dataset CFAR10. After that, we unzip the CFAR and we go to for this file cannot open CFAR. We did this first, then we move to another solution, which is importing directly our data CFAR10 from already predefined library using a TensorFlow Keras dataset and import CFAR. So we imported libraries NumPy for handling arrays, matplotlib for plotting images, and Keras for TensorFlow to load our dataset. Then this code, we load the CFAR10 dataset from Keras. Here it is, xtest, ytest. The function actually returns two sets of data, training and one for testing. The first pair for training is empty, represent the training data, which is not using here. So we discard it by assigning to it this one here. The second pair is for testing, which contain the test images and their corresponding labels. There are images that will be visualizing. Next, we selected 10 randomly images from the set using NumPy random choice. Then we also created library mapping dictionary to associate represented by integers from 0 to 9. Here is airplane, automobile, tilt track, and then I use matplotlib to plot these 10 random images arranged in a 2-row by 5-column grid. Each image is displayed alongside with each label. With each label, here it is, the result. Finally, I use plot show to plot this to visualize the CFAR10 test set. Then we move on to the next code. I'll let my friend Maria finish.
Now let's take a closer look at the code where we define and train our convolutional neural network on the CFAR10 dataset. We begin by importing essential libraries, TensorFlow for building and training our model, Keras layers for defining the architecture, and Adam optimizer for training, and matplotlib for visualizations. Next, we load the CFAR10 dataset using this line. Here, the CFAR10 load data function returns two sets of data, one for training and one for testing. The first pair contains the training data, which we're not using here, so we discard it by assigning it to the variable. The second pair contains the test sets, the images and their corresponding labels that we'll use for evaluation. Once we've uploaded datasets, we normalize the pixel values of the images to the range 0-1 by dividing them by 255. This is important for faster training and better model performance. We also need to one-hot encode labels using the toCategorical function. This converts the class labels into binary vectors, making them compatible for classification tasks. Since the CFAR10 has 10 classes, each label becomes a vector of length 10. Now we enhance the diversity of the training data. We apply that data augmentation. The image data generator class allows us to randomly transform the images by rotating, shifting, shearing, zooming, and flipping them during training. This helps prevent overfitting and makes the model more robust. The augmentation is applied to the training data using datagen.fit. Next, we define the CNN architecture using Keras sequential API. The model starts with a conv2d layer with 32 filters, followed by batch normalization to stabilize and speed up training. ReLU activation is applied to introduce nonlinearity, and max pooling reduces the spatial dimensions. We then proceed to add more layers, and in the following parts of the code, which I'll explain further in the next step, we'll define the rest of the architecture, optimizers, and the learning rate schedule. For the results, we have epoch 1. This means the training has complete epoch 1 out of total 30. We have accuracy first 0.4106. The val accuracy is 0.48, and the accuracy kept increasing until it reached 0.7769, and also the val accuracy reached 0.8. It increased, of course, and for the learning rate, the training loss, it decreased until it reached 0.5763.
Now that we've trained the model, let's move on evaluating its performance. We use the Keras evaluate method. This evaluates the models on test mode and on test loss and test accuracy. The variables is 2, I guess, yes, 2. And the arguments provide detailed output showing the time taken for each step. The test accuracy is a direct measure on how well the model performs. Next, we calculate the F1 score using these lines. And here the model predicts X-test, generate the predictions probabilities for each class, and then we use the NP, the NP argmax to get the class with the highest probability for each prediction, as well as the true class for Y-test. The F1 score is calculated using scikit-learn F1 score function, which provides the balance of precision and recall. And we use the average weighted parameter, which take into account the imbalanced data set. And from the output, we can see that the test accuracy is 0.8 and the test F1 score is 0.79, which shows a strong balance between precision and recall, indicating that the model performs very well. Now let's move to the other code with Mohammed.
We introduced the learning scheduler callback and we add some additional layers, this is considered as a hyperparameter. We import our libraries TensorFlow, TensorFlow Keras, layers like dense, the convolutional 2D, the flatten, max pooling, and batch for normalization, and our activation function. So let's walk through the code. For classifying image from the CFAR10 dataset, we load and pre-process data here in X training, Y training, X test, Y test. We load in the CFAR10 data containing 16,000 color image across 10 classes. The load data function return to dataset, once for training, once for testing. To make sure our model will train faster and perform better, we normalize. Here is we divide over 255. Then we categorize, as we said, data augmentation. Then we move to define the model with the batch normalization. Here we use activation function RU, which takes maximum 0 to plus infinity. It's a mathematical function. If the output is negative, it takes 0. Else it takes its maximum. Then we did the maximum pooling, and we defined the learning schedule. The schedule, if the epoch is greater than 10, we set it to learning rate times the previous learning rate times 0.1. Then we use optimizer and training setup. We're using Adam Optimizer, which is known for like adapting learning rate, and additionally you can add learning rate scheduler callback to adjust learning rate with time, as here in the outputs. We adjust learning from 0.1 to 10 to the power minus 4 as we go, as we reach the epoch 13. The training and validation accuracy, we saw that we went from 0 to 18% in the validation accuracy, and training accuracy is reached 0.78. The training loss and validation, the loss reached 0.05. Then we move to the next one.
Now let's move on to building a more robust convolutional neural network using the CFR10 dataset. This time we'll add some regularization techniques like dropout and L2 to improve generalization and avoid overfitting. First we have loading and processing data. Then we have data augmentation. We already talked about 2 steps. Define the model with batch normalization and dropouts. We compile the model with Adam optimizer and initial learning rate. We define the learning rate schedule. Train the model, save the model, and after defining the architecture, we chose categorical growth entropy as the loss function because we're dealing with multi-class classification. Accuracy is used as the evaluation metric. Finally, we use the fit method to train the model, passing in the augmented data from DataGen. And this is a high-level overview of how do we define and train our CNN with regularization technique and data augmentation to improve performance on the CFR10 data sets. And we have here 2 graphs. Accuracy has improved. Until epoch 30, we have it reached 0.69, and also for the loss, we have it decreased until it reached 0.73. Let's move to the next.
Now moving to using the model to predict on different number of batches and computing overall accuracy. We train the model. We repeat the same steps basically. We always have the CIFAR10 data set. We train it into a copy display. We test it, and then we normalize pixels to be between 0 and 1. So we divide by 255 pixels that we have. We convert this class vector into binary class matrices to work with it in our training. We load the pre-trained model that we had previously, and we define the label mapping. Then we choose a random index from the test case. We make prediction using the loaded model for a batch of images. We adjust the batch size as needed, and then we map the predicted class indices to what label we have. We calculate the accuracy for each prediction to know what is our picture is about. We calculate the overall accuracy to know how accurate is our picture. In this case, it may be not clear to our eyes, but it is there. Let's see how they said. So we have here frog, deer, but the highest accuracy is for the deer, which is 80%. The image is not that clear, but however, our model could predict there is a deer. And we have accuracy 0, 1 for dog, 1 deer, and this is our case. We got it by dividing 1 over Muhim. Installing for the next code, it is the scenario. First we install the Keras tuner, and then we have the hyperparameter tuner as I explained. We had here a problem is we're rerunning our code. Since it took too much time, we had first a lot of tries, 66 trials, and by mistake we restarted the whole process. So just wait until we have a big number of tries to have a bigger accuracy, and then we will continue. I will leave the floor for we will re-explain this.
Okay. So here we used more many hyperparameters tuning as we need to increase. This is due to increasing our value accuracy. Since adjusting more hyperparameters like doing different activation functions and adding more layers and number of neurons in each hidden layer, and adjusting the biases and the weights can affect the accuracy. So this is what we did in training our CFR10 dataset here. So we load the dataset, we encode, we use one hot encoder, then we set up a Keras tuner function to optimize the model hyperparameters such as like the number of filters in the convolutional layer. By defining search space for this parameter, we can automatically tune the model to find the best performance configuration. This approach to improve the model's accuracy, as I said. and which helps us with achieve better performance on classification task. We move on to this. Just like this is the CNN for image classification using our dataset with Keras. We repeat the same steps. Then we set our hyperparameter, the filter 64, the learning rate we adjust it. We use Adam optimizer, build the sequential model. We define our learning rate. Then in terms of optimization, we use multiple optimizer like Adams and CHD and NADAM. The exact choice of optimizer and that parameter, like the number of filters of convolutional layer, will be like optimized using Keras tuner to define the best configuration for image classification. This approach combines like data augmentation, hyperparameter, and regularization to improve the model performance for classifying images. And here is the results. 14 epochs. We reached an accuracy of 0.7291. And like in this plot using matplotlib, it's not as we expected, but when I ran it in my computer, I got better accuracy. It went to 0.8, and the tuning accuracy I can show you in the report the accurate plot for this training. And then we saw that the learning rate we adjusted, and the value lost went to 0.77. Now we move on to training model.
The script set up a deep learning pipeline for training a convolutional neural network and on the Cypher-10 dataset using Keras. Here is a breakdown of the steps. We have dataset loading and preprocessing, data augmentation, model hyperparameters, training combinations, etc. And for the next code, we have the script demonstrates how to load a pre-trained model, use it for predictions, and visualize the results using the Cypher-10 datasets. Here is a step-by-step explanation again. We have done again the same steps. We loaded and pre-processed the Cypher-10 dataset. We then loaded the pre-trained model. We did here label mapping, as you can see, 0 for a plane, 1, etc. Random image selection and visualization, and finally batch prediction. A batch of random images is selected from the test set. The batch size, of course, can be adjusted, and these images are used for prediction. As we can see here, we first got truck, then frog, then horse, then dog, and then we finally got horse. Predicted label horse accuracy, we reached accuracy 1, and overall accuracy for the batch was 80%.
Moving now to the last code, which is not the last code, the before last code. So it is the same thing repeated. We have also we load the data set. We normalize the pixels between 0 and 1. So we divide by 25. We convert the class vectors. We load the pre-trained model that we had previously. Then we calculate the accuracy, and we calculate the overall accuracy. So when compiling the loaded model, the compile matrix give us like an accuracy of 76%, which is kind of good. Moving now to the last code.
So here we display our confusion matrix. Like we import our panda as PG. Panda is used to manipulate data and create data frame. Seaborn here we imported for visualizing our confusion matrix. And the confusion matrix from sklearn matrix is used to compute like our CM, which evaluate the performance of the classification model. Here to explain this, as we label them from 0 to 9. 0 is dog, if I remember. 1 is airplane. 2 is cat. So in each row represent the value accuracy of each image, of each label, and the columns represent the accuracy of of the labels. So we reached here 76.7 for index 0, and for 1 we reached a high accuracy of 904. The more it is, we have a higher number, the more it is accurate. This plot of the confusion for the prediction on the data set showing how well the model perform across different classes. As you can see here, so this is the end of our video representing the classification of images using computer vision and the CNN. Thank you for watching our videos, and we will at the end show you the plot for when it finishes trial 16 or when it elapses the time, and we'll show you the steps and how much accuracy we reach. And thank you.
Thank you so much for your attention. Yeah, have a good day.